Tonight, we're going to travel farther and farther from Earth, crossing the invisible boundaries where spaceflight slowly becomes something much more dangerous. Close to home, astronauts still have layers of protection around them. The International Space Station remains inside much of Earth's magnetic shelter. Mission control can answer within a fraction of a second. Replacement parts can arrive aboard a cargo spacecraft, and an emergency return vehicle is already waiting at the station. But those protections begin disappearing almost as soon as the journey outward begins. Beyond Earth's magnetic field, radiation reaches the spacecraft with far less resistance. Near Mars, a message from home can take more than 20 minutes to arrive. Past Jupiter, sunlight falls to roughly 1/27th of its strength near Earth. At the distance of Voyager One, a command takes nearly a full day to cross the darkness in only one direction. The horror arrives one loss at a time. A broken pump near Earth may be a maintenance problem. On the way to Mars, it could become a mission-threatening emergency. Between the stars, the same failure could happen years before anyone on Earth even receives the message describing it. Every kilometer outward removes another safety net. Fast communication disappears. Rescue becomes impossible. Medical help becomes a set of instructions arriving too late. Power grows harder to produce. Machines must survive longer without replacement, and eventually, turning around may require more energy than the spacecraft has left. By the end of tonight, you're going to understand what a traveler would lose at every major boundary, where the final practical connections to Earth begin to disappear, and why space becomes more horrifying the farther you travel. Before we move beyond orbit, take a moment to like the video and subscribe if you enjoy calm explorations of the universe. It helps this channel continue making long journeys like this one. The best place to begin is only about 400 kilometers above us. At that height, the International Space Station travels at roughly 27,600 kilometers per hour. It completes one orbit in about 90 minutes, carrying its crew around Earth approximately 16 times each day. The station moves through vacuum at a speed that would cross an entire country in minutes. Yet in practical terms, it remains close to home. Radio signals cover the distance between the station and the ground almost instantly. Flight controllers can watch the condition of its electrical system, cooling equipment, atmosphere, computers, and orbit as those systems change. When an alarm appears, specialists on Earth can examine data, compare it with years of engineering records, and help the crew work through the problem. The astronauts are performing the repair, but they are rarely solving it alone. That support reaches beyond advice. Cargo vehicles regularly carry food, clothing, scientific equipment, filters, gases, and replacement hardware into orbit. A failed component does not always need to be repaired forever. It may only need to remain usable until another spacecraft arrives with a new one. The station can survive certain losses because a supply chain still connects it to factories, laboratories, and warehouses on the surface. A return path is also kept beside the crew. A human-rated spacecraft remains docked with enough seats for the people aboard. If the station develops a serious pressure leak, fire, collision risk, or another emergency that makes continued habitation unsafe, the crew does not need to wait for a rescue mission to launch. Their vehicle home is already attached. None of this makes low Earth orbit harmless. The station depends on a large collection of pumps, valves, fans, batteries, computers, solar arrays, radiators, pressure seals, and life support equipment. Small fragments of orbital debris can threaten its hull. Radiation exposure is higher than it is on the ground. A fire inside a sealed spacecraft remains extremely dangerous, and every return through the atmosphere carries risk. What changes the outcome is the amount of help surrounding those dangers. A cooling pump can be monitored by engineers who helped design it. A blocked filter can be replaced from onboard stores or added to a future cargo manifest. A sick crew member can speak with doctors without waiting several minutes for each sentence to cross space. If the entire station becomes unsafe, Earth is hours away rather than months or years. That makes the International Space Station the last safe orbit in a very specific sense. It is the farthest place where humans have lived continuously, but it still functions as part of an Earth-based system. The station is the visible outpost. The larger machine includes tracking antennas, launch sites, cargo vehicles, mission control rooms, medical teams, manufacturers, and thousands of people who never leave the ground. And even that enormous human network explains only part of the protection. The station also remains inside a much older system, created by the planet long before spacecraft existed. It surrounds Earth, bends the paths of charged particles, and reaches far beyond the atmosphere below. Before the journey can move outward, we need to understand the invisible shield the astronauts have not fully left behind. Most of that planetary protection begins far below the station, in the layers of air spread between orbit and the ground. The International Space Station circles Earth at an altitude of roughly 400 kilometers inside a region called the thermosphere. A trace of atmosphere still exists there. It is thin enough that the station experiences near vacuum, yet dense enough to create a small amount of drag that gradually lowers its orbit. Periodic engine burns are needed to raise the station again. Almost all of the atmosphere lies below it. Those gases perform several forms of protection before radiation can reach the surface. Ozone absorbs much of the ultraviolet light that can damage living tissue. Oxygen and nitrogen stop X-rays high above the ground. Incoming atomic nuclei collide with air molecules and break into showers of smaller particles, leaving the atmosphere to absorb much of their energy before they reach sea level. The station has already moved above most of that material. Its aluminium walls and internal equipment provide some shielding, but the crew no longer has kilometers of air overhead. Another part of Earth's protection still surrounds them. Deep below the surface, liquid iron moves through Earth's outer core. This electrically conducting fluid circulates as heat escapes from the planet's interior. Earth's rotation helps organize that motion, creating a planetary magnetic field through a process called the geodynamo. That field reaches thousands of kilometers into space. Charged particles respond to it because moving electric charges curve as they cross magnetic field lines. A slower particle may be turned aside or guided along the field. A very energetic particle can pass through with less deflection. The result depends on its speed, electrical charge, direction of travel, and the strength of the field at that location. The region controlled by Earth's field is called the magnetosphere. Its shape is constantly altered by the solar wind, a stream of charged particles flowing outward from our star. On the side facing that flow, the magnetosphere is compressed to roughly 60,000 kilometers from Earth under typical conditions. Behind the planet, it stretches into a magnetotail that can extend more than 1 million kilometers into space. Auroras reveal part of this process. Electrons and protons guided toward the polar regions collide with oxygen and nitrogen in the upper atmosphere. Oxygen commonly produces green or red light, while nitrogen can add blue and violet. The glowing curtains seen over northern Canada, Alaska, Scandinavia, and Antarctica are visible evidence that charged particles are being directed by Earth's magnetic field. The protection is uneven. Earth's magnetic axis is tilted and offset from the planet's center, and the field is weaker over part of the South Atlantic. This creates the South Atlantic anomaly, a broad region extending over parts of South America and the Atlantic Ocean, where trapped radiation reaches unusually low altitudes. The station's orbit is inclined by 51.6 degrees, carrying it through this region repeatedly. Astronauts receive a measurable increase in radiation while passing through it. Sensitive instruments aboard satellites are sometimes switched off or placed in protective modes because energetic particles can produce false readings, damage detector pixels, or flip information stored inside computer memory. Altitude also matters. A satellite farther from Earth can spend more time among trapped particles. Latitude changes how strongly the field guides particles toward a spacecraft. Solar activity can expand, compress, or disturb parts of the magnetosphere. Particle energy determines whether the field bends a path significantly or allows the particle to penetrate much farther. For these reasons, remaining inside the magnetosphere does not make low Earth orbit radiation-free. A 6-month station mission can expose an astronaut to roughly 80 to 160 millisieverts, depending on conditions and shielding. Average natural background exposure at Earth's surface is only a few millisieverts per year. The difference remains substantial. Earth's atmosphere and magnetic field reduce the amount and type of radiation reaching the station, while the planet's nearby infrastructure helps crews manage what remains. The astronauts have risen far above the surface while staying within the physical reach of their world. Continuing outward carries them through regions where Earth's magnetic field has trapped energetic particles for long periods. Those regions form the Van Allen belts, the first major radiation environment an outbound crew must deliberately cross. The first spacecraft to reveal these trapped particles was Explorer One, the first satellite launched by the United States. It lifted off from Cape Canaveral on January 31st, 1958, carrying a radiation detector developed by a team led by physicist James Van Allen. The instrument was designed to count energetic particles. During parts of the orbit, however, it reported almost nothing. Researchers initially suspected a malfunction. The detector had actually entered regions where radiation was so intense that the instrument became overwhelmed and temporarily stopped producing useful counts. Later missions confirmed that Earth is surrounded by broad zones of trapped charged particles. They became known as the Van Allen radiation belts. The inner belt begins several hundred kilometers above parts of Earth and extends outward for thousands of kilometers. It contains many energetic protons, including particles produced when cosmic rays strike the upper atmosphere and create unstable neutrons. Some of those neutrons decay into protons that become trapped by Earth's magnetic field. The outer belt lies farther away and contains large populations of high-energy electrons. Its size can change considerably during geomagnetic storms, when activity from the Sun disturbs Earth's magnetic environment. At times, the outer belt can swell, weaken, split into separate regions, or temporarily gain an additional layer. These belts have no solid surface. Their radiation levels vary with altitude, latitude, particle energy, and current space weather. A spacecraft can pass through a relatively mild region, while another route, taken at another time, produces a much larger dose. That variation shaped the Apollo flight paths. The crews did not travel straight through the most intense parts of the belts. Mission planners selected trajectories that crossed thinner regions, and the spacecraft moved through them within a few hours. Radiation dose depends partly on intensity and partly on time. Spending several minutes in an elevated radiation field produces a smaller accumulated dose than remaining there for days. Shielding inside the command module reduced exposure further, while continuous monitoring of solar activity helped mission teams avoid launching into known severe conditions. The Apollo astronauts therefore crossed the belts without receiving immediately dangerous doses. Their journeys showed that the belts are a serious engineering constraint, rather than an impassable barrier. More than 50 years later, Artemis I carried a much larger collection of radiation instruments during its uncrewed flight around the Moon in 2022. Sensors were distributed throughout the Orion capsule to measure how radiation changed from one location to another. Two human-shaped experimental torsos traveled in passenger seats. They were named Helga and Zohar. Each represented an adult female body and contained materials designed to imitate human tissue, bones, and organs. Thousands of small detectors were placed inside them. Zohar wore a protective astrorad vest, while Helga traveled without one. Comparing their measurements allowed researchers to study how much protection the vest offered to radiation-sensitive organs. Orion also carries a practical shelter strategy for solar storms. During a major particle event, astronauts can move into the lower central part of the cabin and arrange food, water, equipment bags, and other stored material around themselves. These supplies already have to be carried, allowing their mass to serve temporarily as additional shielding. The first crewed test of Orion beyond low Earth orbit followed in April of 2026. Artemis II launched on April 1st with 4 astronauts aboard. The mission traveled around the Moon and returned to Earth on April 10th after nearly 10 days in space. At its farthest point, the crew reached 248,655 miles from Earth, setting a new distance record for human travel and passing the record associated with Apollo 13. Throughout the mission, detectors measured the radiation reaching different parts of the cabin and the doses received by the crew. The flight added modern human data to results gathered by Apollo, Artemis I, and decades of robotic missions. The radiation belts can be crossed because the route is chosen carefully. The spacecraft provides shielding, and the time inside the strongest regions remains limited. Every part of that protection depends on planning before departure. Beyond the belts, the crew can no longer reduce exposure by completing the crossing within a few hours. The Moon keeps them outside most of Earth's magnetic shelter for days, while the nearest replacement part remains hundreds of thousands of kilometers away. At the Moon, distance begins changing what help can accomplish. The average separation between Earth and the Moon is about 384,400 kilometers. Because the Moon follows a slightly stretched orbit, that distance varies by tens of thousands of kilometers during each month. A radio signal usually takes about 1.3 seconds to travel from one world to the other. That delay is noticeable during conversation. A person may begin replying before hearing the end of the previous sentence. Even so, engineers on Earth can still follow an unfolding problem almost as it happens. Instrument readings arrive within seconds. Calculations can be checked quickly, and new instructions can be transmitted while the situation is still developing. Physical assistance moves at a very different speed. A spacecraft traveling between Earth and the Moon needs several days to complete the journey. No replacement vehicle could reach a lunar crew during the first minutes or hours of a serious emergency. The importance of that difference became clear during Apollo 13. The mission launched from Florida on April 11, 1970, carrying Jim Lovell, Jack Swigert, and Fred Hayes. Their destination was the Fra Mauro Highlands on the Moon. About 56 hours after launch, while the spacecraft was more than 300,000 kilometers from Earth, an oxygen tank inside the service module failed. The accident damaged the second oxygen tank and caused oxygen to escape into space. The command module depended on those tanks for breathable oxygen and for the fuel cells that generated electricity and water. As pressure readings fell, the planned lunar landing ended, and the spacecraft became a survival system with a rapidly shrinking supply of power. The crew shut down most of the command module to preserve its batteries for re-entry. They moved into the lunar module Aquarius, which had been designed to carry 2 astronauts from lunar orbit to the surface and back. It now had to support 3 people during the journey around the moon and home. Aquarius had been intended to sustain 2 astronauts for roughly 2 days. It supported 3 astronauts for close to 4 days. That extra person changed the atmosphere inside the cabin. Lithium hydroxide canisters removed carbon dioxide from the air, but the lunar module used round canisters, while replacement canisters from the command module were square. Rising carbon dioxide could eventually cause headaches, confusion, unconsciousness, and death. Engineers in Houston gathered materials available aboard the spacecraft and assembled a working adapter on the ground. Their design used items such as plastic bags, cardboard, a suit hose, and tape. The crew followed the transmitted instructions and built the same device inside Aquarius, allowing the command module's square canisters to work with the lunar module's system. Earth supplied the procedure within minutes. Every physical object used in the repair had already crossed the distance with the crew. Trajectory created a second challenge. Apollo 13 had begun its journey on a path that could naturally loop around the moon and return toward Earth. Before the accident, a planned maneuver had shifted the spacecraft away from that simple free return route to support the intended landing at Fra Mauro. Mission controllers calculated new engine burns to restore a safe path. The lunar module's descent engine, originally meant to lower Aquarius toward the moon, was used to alter the course of the entire connected spacecraft. After passing behind the moon, another burn shortened the return journey and adjusted the landing point on Earth. Each calculation depended on the engine producing the expected thrust. The guidance system had to remain usable, and the crew had to orient the spacecraft correctly while conserving electricity. Water became tightly rationed. Cabin temperatures dropped as equipment was switched off. Moisture condensed on the cold interior surfaces. Mission control remained closely involved throughout the crisis. Specialists calculated power-up procedures, checked consumable levels, tested repairs, and prepared the command module for re-entry. The crew heard their voices with only a brief pause. Those voices could guide the astronauts through equipment they already possessed. They could not deliver another oxygen tank, another battery, or another engine. Apollo 13 returned safely on April 17, 1970, after traveling around the moon without landing. Its survival showed how much can still be accomplished when communication remains nearly immediate and a workable route home still exists. Near Mars, the same radio exchange stretches from seconds into minutes. An emergency can change completely before Earth even receives the first description of what happened. Mars never remains at one fixed distance from Earth. Both planets travel around the Sun at different speeds, following separate orbits that bring them closer together and then carry them far apart again. Earth completes one orbit in about 365 days. Mars needs roughly 687. At their closest favorable approaches, the planets may be separated by less than 60 million kilometers. When they occupy opposite sides of their orbits, the gap can grow beyond 400 million kilometers. Radio waves travel at the speed of light, close to 300,000 kilometers per second. Even at that speed, a message usually needs somewhere between about 3 and 22 minutes to travel from Earth to Mars. A question sent during the longest delays may not receive an answer for roughly 44 minutes. That limit comes from distance itself. A larger antenna can collect a weaker signal. More transmitter power can improve reception, while better compression can place more information into the transmission. None of those improvements can make the signal arrive sooner than light allows. Robotic missions already operate around this delay. Perseverance landed inside Jezero crater on February 18, 2021. Its controllers at NASA's Jet Propulsion Laboratory do not steer it continuously with a joystick. The rover's position, images, and engineering data first travel from Mars to Earth. Scientists and engineers then study the terrain, choose targets, prepare commands, and send a plan back across interplanetary space. A transmitted plan may tell Perseverance where to drive, which rock to examine, and when to operate an instrument. Onboard computers handle the immediate details. Cameras observe the ground ahead, and autonomous navigation software identifies rocks, slopes, or other hazards that the rover should avoid. This independence allows Perseverance to travel farther during a Martian day than earlier rovers could manage under more cautious command methods. It also reflects a basic fact of Mars exploration. The rover cannot stop beside every stone and wait for a human decision. Landing requires much greater autonomy. When Perseverance reached Mars, it entered the atmosphere at close to 19,500 kilometers per hour. Over approximately 7 minutes, it had to slow through atmospheric drag, deploy a parachute, discard its heat shield, measure the ground below, select a safe landing area, and descend beneath a rocket-powered platform. During the final stage, the platform lowered the rover on cables in a maneuver known as the sky crane. Perseverance touched the ground, the cables were cut, and the descent stage flew away to crash at a safe distance. Every important decision occurred on board. Mars was more than 11 light minutes from Earth at the time. By the moment Mission Control received confirmation that atmospheric entry had begun, the rover had already landed successfully or had been lost. Human crews would experience the same delay during much less predictable events. A pressure sensor might report a cabin leak. Smoke could appear behind an equipment panel. A crew member could suffer a serious injury while another astronaut is outside the habitat. Electrical power might fail during a dust storm when solar generation is already reduced. The first response would come from the people present. They would isolate damaged equipment, identify the source of the problem, and decide which systems could be shut down safely. Earth-based specialists could study the transmitted data and offer detailed advice later, but their guidance would arrive after the crew had already made the earliest and most urgent decisions. Communication may become even less reliable during Mars solar conjunction. This occurs when Earth and Mars pass to opposite sides of our star, placing the brightest region of the solar system near the radio path between them. Charged gas around the Sun can interfere with signals, so mission teams may reduce commanding for roughly 2 weeks and allow spacecraft to follow previously uploaded instructions. A Mars crew would therefore need enough training, software, manuals, and local authority to continue through periods of delayed or limited contact. Mission control would remain valuable, though its role would resemble written consultation more than live supervision. Information can still cross the distance. Physical rescue must obey a much slower set of rules, determined by planetary motion, available propellant, and the spacecraft's existing path through space. A spacecraft traveling toward Mars is already moving sideways through the solar system at enormous speed. Earth circles the Sun at nearly 29.8 kilometers per second. Mars moves more slowly, at roughly 24.1 kilometers per second. A vehicle leaving Earth begins with Earth's orbital motion, then uses its engines to change that motion enough to enter a new path that intersects the future position of Mars. The destination is therefore a moving point. Mission planners must calculate where Mars will be months after launch and place the spacecraft on a trajectory that reaches the same region at the same time. The most efficient opportunities occur approximately every 26 months, or about 780 days. During each window, Earth and Mars reach a favorable arrangement for a transfer using a manageable amount of propellant. A common reference is the Hohmann transfer. an elliptical path connecting two roughly circular planetary orbits. A minimum energy Hohmann transfer from Earth's orbit to Mars takes about 8.5 months. Actual mission plans may use somewhat faster or slower routes, depending on available fuel, spacecraft mass, radiation exposure, life support limits, and arrival requirements. This geometry explains why turning around is more complicated than rotating the spacecraft. Small thrusters can point the vehicle in a new direction. Its existing momentum continues, carrying it along the original path, until an engine produces enough thrust to alter that motion. A spacecraft could face Earth while still traveling rapidly away from it. Engineers describe the ability to change velocity using the term delta V. Delta means change. So delta V is simply a measurement of how much a spacecraft can alter its speed and direction. Each departure burn, course correction, orbital insertion, landing maneuver, and return burn consumes part of the mission's available delta V. Propellant creates the change by being expelled from the engine at high speed. The spacecraft moves in the opposite direction. Once that material has been used, it cannot be recovered during the flight. Carrying additional propellant helps, though it creates a compounding mass problem. The launch vehicle must accelerate the fuel needed for later burns. That extra fuel requires larger tanks and stronger structure, adding still more weight. More launch propellant is then needed to accelerate the tanks, structure, and future propellant together. This relationship is described by the rocket equation. It places a severe cost on large velocity changes, especially when a spacecraft must carry everything from Earth. Mission plans therefore separate several forms of return. A planned return is built into the original architecture. The crew follows a prepared schedule, leaves Mars when the planets reach the required alignment, and uses a vehicle reserved for the journey home. An abort changes that plan after a failure. Depending on when the problem occurs, the crew might return toward Earth, continue toward Mars, enter a different orbit, or follow a long path through the inner solar system before reaching home. A rescue mission would require another spacecraft to launch after the emergency, follow the crew's trajectory, match its speed, and carry enough resources for the encounter and return. Catching a moving vehicle becomes increasingly difficult as the distance grows. Early in a Mars journey, some mission designs preserve abort paths that could eventually bring the crew back. Even these returns may take many months. Later in the flight, the spacecraft may have traveled far enough that continuing toward Mars uses less propellant than reversing course. System health matters as much as position. An intact propulsion system may still perform a major correction. A damaged engine, leaking tank, or failed navigation sensor can remove that option even when a return path exists mathematically. Planetary geometry also limits departure from Mars. Conjunction-class missions use relatively efficient trajectories and usually include a long stay near the planet, often around 500 days, while Earth and Mars move into position for the return. Including the outbound and inbound journeys, the complete expedition may last roughly 2.5 years. A crew experiencing a serious failure during that stay could remain unable to leave immediately. Their return vehicle might be healthy and fully fueled, yet the available trajectory could require more propellant than it carries. Earth would remain present in navigation displays and scheduled conversations. Its location could be calculated with great precision. Physical access would depend on engines, fuel, functioning hardware, and the current arrangement of the planets. Once rapid return disappears, the spacecraft becomes the crew's environment for months at a time. During every one of those months, radiation continues passing through the hull and adding to the dose already stored within the body. During a Mars journey, radiation exposure continues whether the crew is working, sleeping, or waiting for the planets to move into a better position. Two main sources shape that environment. The first comes from solar activity. Flares and eruptions can accelerate charged particles away from the sun at high speed. These events are often called solar particle events. Many of the particles are protons, and a strong event can raise radiation levels around a spacecraft within hours. The second source arrives from much farther away. Galactic cosmic rays enter the solar system from the wider galaxy. They include protons, helium nuclei, and heavier atomic nuclei that have lost all of their electrons. A nucleus without electrons carries a strong positive charge, allowing it to damage material as it passes through a spacecraft and through human tissue. Solar events arrive in bursts. Galactic cosmic rays form a nearly continuous background. NASA measured that background directly during the voyage of the Curiosity rover. Curiosity launched toward Mars in November of 2011 and traveled inside a protective cruise stage for about 8.5 months. Its radiation assessment detector recorded the particle environment throughout the trip. The average dose produced by galactic cosmic rays was approximately 1.8 millisieverts per day. A millisievert is a unit used to estimate the biological effect of ionizing radiation. It accounts for the amount of energy deposited in tissue, and for the fact that some forms of radiation cause more biological damage than others. Curiosity traveled during a relatively quiet period of solar activity. Solar particles contributed only about 3% of the measured cruise dose during that particular journey. A crew departing during different solar conditions could experience a different balance. The solar cycle lasts about 11 years. Near solar maximum, eruptions and particle storms become more common. The stronger solar magnetic field can also reduce part of the incoming galactic cosmic ray population. Near solar minimum, major solar storms are generally less frequent, while galactic cosmic ray exposure can rise. Mission planners, therefore, cannot select one season that removes both hazards. Solar particle events may allow some warning. Spacecraft near the sun can detect an eruption, and instruments can monitor changing radiation levels. A crew could move into a compact shelter positioned near the center of the vehicle. Water containers can be placed around that shelter. Food packages, equipment, and other supplies add more mass between the astronauts and the incoming particles. Materials rich in hydrogen are especially useful because hydrogen nuclei can slow many charged particles without producing as much secondary radiation as some heavier shielding materials. Galactic cosmic rays are harder to control. Their most energetic particles can penetrate thick layers of material. Some are heavy nuclei, traveling close to the speed of light. When one of these nuclei strikes aluminium or another shielding material, the collision can break the nucleus apart. The fragments continue through the spacecraft as a shower of smaller particles. This process is called nuclear fragmentation. The shield absorbs part of the original energy, while the collision creates additional radiation inside the vehicle. Adding more dense material can still provide protection, though the benefit depends on its composition, thickness, and the energy of the incoming particle. Radiation becomes harmful because it removes electrons from atoms and molecules inside the body. This process is called ionization. It can break chemical bonds, alter proteins, and damage DNA. Cells repair much of this damage successfully. Some damaged cells die and are replaced. Other changes may remain and increase the chance of cancer years later. Long exposure may also raise the risk of cataracts and cardiovascular disease. Researchers continue studying possible effects on the brain and central nervous system. Animal experiments have found changes after exposure to some high-energy particles, though the long-term cognitive risk to astronauts remains uncertain because very few people have experienced deep space radiation. Dose also changes with route and shielding. A crewed spacecraft may provide more protection than Curiosity's cruise stage. A faster journey would shorten the exposure period. A solar storm encountered at the wrong time could add a large dose over a much shorter interval. The danger therefore builds through accumulation. Most galactic cosmic rays pass through the spacecraft without creating a visible event. No cabin alarm sounds for each damaged molecule. The crew may feel healthy, while the total recorded by their dosimeters rises day after day. Radiation is only one process acting throughout the voyage. Even inside a perfectly shielded cabin, the absence of normal gravity would begin changing bones, muscles, circulation, and vision within the first weeks. Inside the spacecraft, the human body begins adjusting to an environment it has never encountered during its evolutionary history. On Earth, gravity places a constant load on the skeleton. Standing, walking, and climbing stairs all require bones to support weight while muscles pull against resistance. Bone tissue responds to those forces by continually rebuilding itself. In microgravity, much of that load disappears. The body begins removing mineral from bones that no longer seem to need their former strength. The greatest losses tend to occur in weight-bearing areas such as the hips, pelvis, and lower spine. Without effective countermeasures, astronauts can lose roughly 1% or more of their bone mineral density in some regions during each month of flight. Calcium released from bone enters the bloodstream and is later removed through the kidneys. This can raise the chance of developing kidney stones, which would be especially difficult to treat during a distant mission. Muscles change for a similar reason. The calves, thighs, back, and muscles that normally hold the body upright receive far less work. Muscle fibers shrink, strength declines, and endurance falls unless astronauts exercise intensively. Crews aboard the International Space Station usually spend around 2 hours each day exercising. A resistance machine uses vacuum cylinders to imitate the load of weights. Astronauts also run while held against a treadmill by straps and use a stationary cycle for cardiovascular training. These systems reduce the losses, though they do not reproduce every effect of gravity. Exercise equipment also occupies space, consumes power, and requires maintenance. A broken resistance machine on a multi-year voyage would become a medical problem long before the crew could replace it. Weightlessness changes the movement of fluid as well. On Earth, gravity pulls blood and other fluids toward the legs. In orbit, roughly 1 to 2 liters can shift toward the chest and head during the first days of flight. This creates the swollen face and thinner-looking legs, often seen in new astronauts. The body initially interprets the upper body fluid increase as excess volume and removes some water and salt. Blood volume can fall as a result. The pressure changes inside the head may also affect the eyes. Some astronauts develop a condition called spaceflight-associated neuroocular syndrome. Neuroocular refers to the connection between the nervous system and the eye. Observed changes can include flattening at the back of the eyeball, swelling around the optic nerve, and folds in the layer containing blood vessels behind the retina. Some astronauts experience changes in near vision that continue after returning to Earth. The exact cause remains under investigation, and individual susceptibility varies. The cardiovascular system also adapts. The heart no longer needs to pump blood upward from the legs against normal gravity. Over time, it becomes accustomed to a different pressure pattern and a lower circulating blood volume. When astronauts return to the ground, gravity suddenly pulls blood downward again. Some become dizzy when standing, because the body cannot immediately maintain enough blood flow to the brain. Reduced exercise capacity and faintness can continue during the first days of recovery. Balance is affected through the vestibular system inside the inner ear. Small organs there normally sense gravity and linear acceleration. In orbit, they receive no stable downward signal, while the eyes continue reporting movement and orientation. The brain gradually learns to interpret this unusual combination. Returning to gravity requires a second period of adaptation. Astronauts may feel unsteady, misjudge motion, or have difficulty walking normally after landing. A Mars crew would face an additional uncertainty. Gravity on the Moon is about 16.5% as strong as Earth's. Mars provides roughly 38%. Human beings have spent days on the lunar surface, but nobody has lived for months under lunar or Martian gravity. Researchers therefore do not know whether 38% of Earth gravity would preserve most bone and muscle, slow the losses, or merely produce a different form of decline. A rotating spacecraft could create artificial gravity. As the habitat spins, the floor pushes inward on the crew, producing a sensation similar to weight. A larger rotating radius can provide useful gravity with a slower and more comfortable rotation rate. A smaller habitat must spin faster, increasing dizziness and unusual sideways forces when someone moves inside it. Creating that rotating structure would add mass, bearings, seals, and mechanical complexity to the vehicle. NASA includes altered gravity among the central hazards of human exploration, because every long journey must preserve bodies designed for Earth. Doing so requires a complete artificial environment whose air, water, pressure, temperature, food supply, and waste systems remain active every hour of the mission. A spacecraft must continually rebuild the environment its crew uses up. Breathing removes oxygen from the cabin and replaces it with carbon dioxide, heat, and water vapor. Drinking moves stored water into the body before some of it returns through urine, sweat, and exhaled moisture. Cooking, washing, plant growth, and equipment cooling distribute the same limited supply through many different parts of the habitat. On Earth, these materials pass through oceans, soil, plants, weather systems, and treatment facilities. A spacecraft has to compress portions of that planetary cycle into machinery small enough to launch. Aboard the International Space Station, this work is handled by the Environmental Control and Life Support System. Its equipment regulates cabin pressure, removes carbon dioxide, produces oxygen, controls humidity, processes wastewater, and filters trace chemicals released by people and equipment. Moisture from an astronaut's breath and skin condenses inside the station's ventilation system. Instead of allowing that water to collect on walls or disappear into waste storage, the system captures it as humidity condensate and sends it for treatment. Urine follows a separate path through the urine processor assembly. The liquid is heated under reduced pressure, allowing much of the water to evaporate at a lower temperature. That vapor is separated from concentrated waste and condensed again. The remaining brine still contains usable water. Brine is the highly concentrated liquid left after most of the easier water has been removed. For many years, part of that moisture could not be recovered efficiently aboard the station. A newer brine processor assembly improved the process. It uses special membranes and warm, dry air to pull additional water from the leftover brine. After this upgrade, NASA demonstrated total water recovery approaching 98%. The recovered liquid then enters the water processor assembly. Filters remove particles and dissolved contaminants. A catalytic reactor uses heat and oxygen to break down small organic chemicals that remain. Sensors examine the finished water before it returns to storage for drinking, food preparation, and oxygen production. A recovery rate near 98% is a major engineering achievement. It also means that roughly 2 units remain unavailable for every 100 units passing through the complete cycle. On a 6-month station expedition, losses can be replaced by stored reserves and later cargo deliveries. During a voyage lasting several years, the the same small percentage compounds. A multigenerational vessel could not depend on regular tanks of replacement water arriving from Earth. Some losses occur because water remains trapped in filters, concentrated waste, food packaging, plant tissue, cleaning materials, or inaccessible chemical compounds. Maintenance can spill small amounts. Airlock operations may release humid cabin air into space. Each loss is minor by itself, though a closed habitat must account for all of them over time. Oxygen also moves through a cycle. The station can split purified water through electrolysis, a process that passes electricity through water molecules and separates them into hydrogen and oxygen. The oxygen enters the cabin atmosphere. The hydrogen can be combined with carbon dioxide removed from the crew's air. Inside a Sabatier reactor, these gases produce water and methane. The water returns to the life support system, recovering part of the oxygen and hydrogen that would otherwise be lost. Methane is generally discarded because extracting its hydrogen requires additional equipment and energy. Each stage depends on physical hardware. Membranes can become coated with contaminants. Catalysts slowly lose effectiveness. Pumps wear as internal surfaces move against one another. Filters collect material until airflow or water flow becomes restricted. Sensors may drift, meaning their readings gradually become less accurate even though the instrument continues operating. A recycling percentage therefore describes the performance of an entire chain rather than a permanent property of the spacecraft. The loop remains nearly closed only while every important link stays powered, calibrated, cleaned, and repaired. Food presents an even harder problem. Water molecules can be purified repeatedly without changing their basic identity. A complete food cycle would need to recover carbon, nitrogen, phosphorus, and other nutrients from human waste and dead plant material, then return them safely to new crops. Plants would also require light, growing space, temperature control, pollination, and protection from disease. A failed crop could remove both food and part of the system used to refresh the air. Deep space survival depends on reclaiming the same limited material many times. The crew may recognize the water in a drinking pouch, while its earlier forms could have included cabin humidity, wastewater, or moisture recovered from concentrated brine. When part of that cycle fails, the problem quickly crosses from engineering into medicine. Far from Earth, the people who diagnose the crew and the people who repair the habitat must already be aboard. A closed habitat can recycle air and water, yet it cannot guarantee that every person inside will remain healthy. Astronauts assigned to the International Space Station undergo extensive medical screening before launch. Doctors look for conditions that could become dangerous in orbit, including heart problems, unstable vision, kidney stones, and dental disease. The goal is to reduce the chance that a hidden problem will appear during the mission. Once aboard, the crew has medical kits containing medications, bandages, intravenous supplies, emergency equipment, and tools for examining injuries or illness. At least 2 crew members usually receive additional medical training, even when neither is a physician. Flight surgeons on Earth can speak with them almost immediately. These doctors review symptoms, vital signs, images, and test results, while specialists from other fields can join the consultation when needed. Ultrasound has become especially useful in orbit because a large X-ray or magnetic resonance scanner cannot be carried easily aboard the station. An astronaut can place a handheld ultrasound probe against the body, while a doctor on Earth watches the images and provides guidance. Crews have used this method to examine muscles, blood vessels, internal organs, and possible injuries. A serious case still has access to evacuation. A docked return vehicle can carry the patient back through the atmosphere, where ambulances, hospitals, operating rooms, and specialist teams are waiting. That medical structure changes during a Mars mission. At the greatest communication delays, a crew member could report severe abdominal pain and wait more than 20 minutes for the message to reach Earth. A doctor might study the information immediately, yet their response would require another 20 minutes to return. By then, the patient's blood pressure, pain, or level of consciousness could have changed. Some conditions allow time for consultation. Others demand action within minutes. A severe allergic reaction may obstruct breathing. Internal bleeding can continue without producing an obvious wound. A burn inside the habitat may involve damaged tissue along with smoke inhalation. A fractured bone could threaten nearby blood vessels or prevent a crew member from performing essential work. Kidney stones are especially relevant because bone loss in microgravity can release calcium into the bloodstream and urine. A small stone may pass on its own. A blocked urinary tract can cause intense pain, infection, and kidney damage. Dental problems create a different challenge. A cracked tooth or deep infection may require drainage, extraction, pain control, and antibiotics. On Earth, a dentist can take detailed images, sterilize instruments, choose among several treatments, and arrange further care. A distant crew would work with a limited set of tools and whatever training had been completed before launch. Appendicitis is often used in exploration planning because treatment may require surgery. Performing an operation inside a spacecraft involves anesthesia, sterile equipment, reliable monitoring, trained assistance, and a safe recovery area. Blood for transfusion is difficult to store for long periods, while the crew may be too small to provide a compatible donor without creating another medical risk. Terrestrial medicine remains dependable, partly because it is spread across many layers. A local clinic can send samples to a laboratory. A hospital can call a surgeon, cardiologist, or infectious disease specialist. Pharmacies and blood banks replace supplies as they are used. A Mars habitat would have to compress parts of that network into a few rooms. No small crew can include a specialist for every organ system, and medical duties may fall to someone who is also responsible for life support, navigation, or power systems. The supplies themselves continue aging. Medications have different shelf lives depending on their chemical formulation, temperature, humidity, packaging, and exposure to radiation. Tablets, liquids, injectable drugs, and biological medicines do not all degrade at the same rate. A label may remain readable long after the active ingredient has weakened or broken into unwanted compounds. Sterile dressings can lose their seals. Diagnostic sensors drift out of calibration. Batteries inside portable equipment slowly discharge. Plastic tubing and rubber seals can become brittle over years. Future missions may carry software that compares symptoms with medical records, compact laboratory devices, and robotic tools that assist with precise procedures. Some drugs might eventually be produced on board from stored chemical ingredients or engineered microorganisms. Broad medical training would still be essential because automated systems can fail, and unusual cases rarely follow a perfect checklist. For much of a Mars expedition, evacuation would require months rather than hours. Treatment, monitoring, and recovery would all occur inside the same habitat that must continue operating around the patient. The medical equipment supporting that care will age alongside every pump, fan, valve, computer, and pressure seal aboard the spacecraft. Keeping the crew alive eventually depends on the ability to repair much more than the human body. Every piece of equipment aboard a spacecraft begins aging before the mission leaves Earth. A bearing slowly loses material where two surfaces meet. Rubber seals harden as heat, radiation, and chemical exposure alter their structure. Lubricants can evaporate, separate, or migrate away from the place where they are needed. Filters collect dust and biological material until airflow begins to fall. Electrical systems degrade in quieter ways. Repeated heating and cooling can fatigue solder joints. Radiation can damage computer memory or cause a stored bit to change value. Sensors may continue producing numbers while gradually drifting away from the true temperature, pressure, or oxygen level. Preventive maintenance tries to find these changes before a failure occurs. Crews inspect equipment, replace parts after a planned number of operating hours, and compare sensor readings over time. Corrective maintenance begins after something has already stopped working. The International Space Station uses both approaches. It stores replacement pumps, fans, valves, filters, cables, and computer components. Cargo vehicles bring additional hardware from Earth, while engineering teams on the ground study unusual readings and prepare repair procedures. A deep space vessel eventually loses all of those advantages. Its stock of spares becomes finite. The people who designed an aging system may be separated from the crew by decades, and the factory that produced a component may no longer exist. Redundancy delays this problem. 2 pumps can be installed where only one is needed, allowing the second to take over after a failure. Several computers can compare results and reject an abnormal reading. Redundant systems can still share a common weakness. This is called a common mode failure. 2 identical pumps may contain the same seal material, manufacturing defect, or software error. Age and radiation can damage both in similar ways. Crews may also cannibalize equipment. A failed science instrument could provide a motor, connector, or circuit board needed by life support. This works only when the parts are compatible and when sacrificing one system does not create a larger problem later. Voyager provides a remarkable example of extending machinery far beyond its expected operating life. Voyager One launched in September of 1977. In 2017, engineers activated 4 trajectory correction thrusters that had not been used since 1980. The thrusters were originally intended for larger course adjustments near the planets. Engineers tested them because the smaller thrusters used to point Voyager's antenna toward Earth were wearing out. After 37 years of inactivity, the backup set still worked. Voyager's survival shows what careful design, redundancy, and patient engineering can accomplish. Its requirements remain modest compared with a crewed ship. Voyager carries no breathable atmosphere, medical bay, food production system, or rotating machinery large enough to support a community. A truly independent vessel would need to produce replacement parts during the journey. The first 3-dimensional printer operated aboard the International Space Station in 2014. It melted a plastic filament and deposited the material in thin layers. Test objects were later compared with matching parts printed on Earth to study how microgravity affected the process. That technology could produce handles, brackets, covers, and simple tools from stored polymer. Metal additive manufacturing could eventually create stronger parts by melting powder or wire with a laser, electric arc, or electron beam. A printed object can look complete while containing hidden weaknesses. Small gaps between layers create porosity, meaning tiny, empty spaces remain inside the material. Cooling conditions affect grain structure, the microscopic arrangement of crystals inside metal. Both can change strength and resistance to repeated loading. Fatigue strength matters because a part may survive one heavy load and later crack after thousands of smaller cycles. Dimensional tolerance also matters. A bearing surface or valve seat may need to match its design within a fraction of a millimeter. Quality control would therefore become part of survival. Ultrasound can search for internal cracks, X-ray imaging can reveal voids. Other forms of non-destructive inspection test a component without cutting it apart or making it unusable. Manufacturing also requires feedstock, cutting tools, furnaces, measurement equipment, and software. Digital design libraries could store thousands of component files, though a file provides little value without the correct material and a working machine. Knowledge must survive with the equipment. Crew members would need to understand machining, metallurgy, inspection, and repair. Each generation would have to teach those skills through practice, because written instructions cannot capture every sound, vibration, or surface change recognized by an experienced technician. Carrying spare parts buys time. Carrying the capacity to create reliable parts gives the ship a chance to remain independent. That capacity demands a steady supply of electricity for workshops, computers, agriculture, medicine, and life support. As the journey continues outward, sunlight begins weakening according to a simple law of distance. That steady electrical demand becomes harder to meet as the spacecraft moves away from Earth. Near our planet, a surface facing directly toward the Sun receives roughly 1,360 watts of solar energy across each square meter before the atmosphere absorbs or scatters any of it. This value is often called the solar constant, although it changes slightly as Earth follows its mildly elliptical orbit. The available energy declines according to the inverse square law. Light spreads outward across an ever-growing spherical area. When the distance doubles, the sphere's surface area becomes 4 times larger, leaving 1/4 as much energy across each square meter. At 3 times the distance, the intensity falls to 1/9. Mars orbits at an average distance of about 1.5 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, close to 149.6 million kilometers. At Mars, a solar panel receives roughly 43% of the energy the same panel would collect near Earth. This reduction already affects mission design. A Martian habitat powered by sunlight would need larger arrays than an equivalent base near Earth. Dust settling on those panels would reduce production further. The global dust storm of 2018 darkened the sky for weeks and ended contact with the Opportunity rover after its batteries could no longer be recharged. Jupiter lies much farther out, at an average distance of about 5.2 astronomical units. Sunlight there is only about 1/27th as intense as it is near Earth, leaving roughly 3.7% of the original power across the same area. NASA's Juno spacecraft demonstrated that solar power can still work at this distance. Juno launched in August of 2011 and entered orbit around Jupiter in July of 2016. Its 3 long solar wings provide about 60 square meters of collecting area. Near Earth, those arrays could have generated around 14,000 watts. At Jupiter, their output was only a few hundred watts. That small electrical budget still had to operate the spacecraft's computers, heaters, communications equipment, and scientific instruments. Juno stores energy in batteries and carefully schedules high-demand activities. Its elongated orbit also means that the arrays experience changing temperatures and radiation conditions during each close pass. Europa Clipper requires an even larger collecting surface. Its 2 solar wings extend more than 14 meters from the central spacecraft on each side, producing a total area greater than 90 square meters. When fully deployed, the vehicle spans roughly the length of a basketball court. Those large wings allow Europa Clipper to generate useful power near Jupiter, though their size creates additional engineering problems. Hinges and motors must unfold them after launch. Long structures flex during maneuvers. Electrical wiring has to carry power across moving joints, and each square meter creates more surface that can be struck by small particles. Solar cells also age. Energetic particles can damage the crystal structure inside the semiconductor material that converts light into electricity. Over years, this radiation damage lowers the amount of current the cells can produce. Engineers launch spacecraft with more generating capacity than they initially need, so the mission can continue after part of that performance has been lost. At Saturn, which averages about 9.5 astronomical units from our star, sunlight falls to a little more than 1% of its near-Earth intensity. At Neptune, almost 30 astronomical units away, the available level is close to 0.1%. Visible darkness does not arrive at the same rate as the engineering problem. Daylight near Jupiter would still appear vastly brighter than a full moon seen from Earth. Human eyes respond well across a wide range of brightness, while a solar panel can collect only the energy that physically reaches its surface. The outer solar system also demands more heating. Electronics, batteries, propellant lines, and mechanical joints must remain within suitable temperature ranges. Weak sunlight contributes less warmth, so part of the limited electrical supply may be spent running heaters that prevent equipment from becoming too cold to function. Every additional watt now requires more panel area, more structure, or an onboard energy source carried from home. The gradual decline appears predictable until the spacecraft reaches Jupiter, where the planet's magnetic environment creates a concentrated danger that distance alone would never reveal. Jupiter changes the character of the journey long before a spacecraft reaches its cloud tops. The planet's magnetic field controls a region of space, millions of kilometers across. On the side facing the Sun, pressure from the solar wind compresses this magnetosphere. Behind Jupiter, the field stretches into a long magnetotail that reaches far beyond the planet and may extend hundreds of millions of kilometers downstream. Jupiter's rapid rotation helps make this environment especially powerful. The planet completes one turn in slightly less than 10 hours, giving it the shortest day of any planet in the solar system. Magnetic field lines sweep around with that rotation and influence electrically charged material caught nearby. Much of that material comes from Io, the innermost of Jupiter's 4 large Galilean moons. Io is the most volcanically active world known. Its volcanoes release sulfur dioxide gas, which spreads away from the moon and becomes broken apart by sunlight and collisions. Some atoms lose electrons and become ions, meaning they carry an electrical charge. Jupiter's magnetic field captures many of these ions and forces them to circulate around the planet. The result is the Io plasma torus, a broad ring of charged sulfur and oxygen particles following Io's orbit. Plasma is a gas whose atoms have been separated into charged ions and free electrons. In this state, the material responds strongly to magnetic and electric fields. Particles inside Jupiter's magnetosphere can gain large amounts of energy. They strike spacecraft surfaces, pass through electronic components, damage solar cells, and change information stored in computer memory. A particle hitting a circuit can produce a temporary error. Repeated exposure can gradually weaken the material itself. NASA's Juno spacecraft was designed around this danger. Juno entered orbit around Jupiter in July of 2016, after traveling for nearly 5 years. Its instruments needed to operate during repeated close passes over the planet's poles, including passages through regions of intense radiation. Many of Juno's most important electronic systems are housed inside a titanium vault near the center of the spacecraft. The enclosure weighs close to 200 kilograms. Its walls are approximately 1 centimeter thick, and more than 20 electronic assemblies are protected inside. Titanium does not stop every incoming particle. The vault greatly reduces the total dose, reaching the computers and power control equipment, allowing them to survive much longer than they would behind ordinary spacecraft panels. The components themselves were also chosen and tested for radiation resistance. Engineers expected some gradual damage, so the mission included shielding margins and software able to handle certain memory errors. Juno's orbit provides an additional layer of protection. It follows a long, stretched path over Jupiter's poles rather than circling close to the planet at all times. Most of each orbit is spent far from the strongest radiation belts. The spacecraft then passes rapidly near Jupiter, gathers measurements, and moves outward again. This approach limits accumulated exposure. Radiation dose depends on intensity and time, just as it did during the earlier crossing of Earth's Van Allen belts. Juno enters a much harsher environment, but it avoids remaining there continuously. Europa Clipper follows the same general principle on a larger scale. Europa travels deep inside Jupiter's radiation system, where energetic particles continually strike its icy surface. A spacecraft placed in a tight orbit around Europa would receive damaging radiation on every circuit. Europa Clipper is instead designed to orbit Jupiter and make dozens of close flybys of the Moon. Each encounter allows its instruments to study Europa's ice, gravity, magnetic response, and possible subsurface ocean before the spacecraft moves away from the most intense region. Orbit selection becomes part of the shielding system. The mission survives through a combination of distance, timing, protected electronics, and carefully chosen paths. Beyond Jupiter, some regions of space contain fewer trapped particles than the area surrounding the giant planet. The physical environment can therefore become locally quieter even as the distance from Earth continues growing. The deeper danger remains in the length of the journey. Once Jupiter's concentrated radiation is left behind, the spacecraft's power source, thermal systems, and electronics must continue functioning through years or decades without repair from home. Far beyond Jupiter, solar panels can still collect a little energy, though their useful output becomes increasingly difficult to justify against their size and mass. Robotic missions traveling into this region often carry their power source with them. Voyager One and Voyager Two, each launched in 1977, with 3 radioisotope thermoelectric generators. Cassini used the same general technology during its 13 years at Saturn. New Horizons relied on it while crossing Pluto's orbit, and the Curiosity and Perseverance rovers use compact versions on the surface of Mars. A radioisotope thermoelectric generator begins with plutonium-238. This material is unstable, so its atomic nuclei gradually decay into more stable forms. Each decay releases energy as heat. The generator surrounds the warm fuel with thermocouples. A thermocouple is made from 2 different conducting materials. When one end remains hot and the other stays cooler, an electric voltage develops between them. This effect converts a portion of the decay heat directly into electricity. No steam turbine has to spin. There is no combustion chamber or chain reaction to control. The generator contains few moving parts, allowing it to operate for decades with little mechanical wear. The electrical output remains modest. Voyager's 3 generators produced roughly 470 watts when each spacecraft launched. That was enough for scientific instruments, communications, computers, and heaters, because an uncrewed probe has no air recycling machinery or living quarters. Curiosity's generator produced around 110 watts of electricity at the beginning of its mission. Waste heat from the unit also circulates through the rover, helping keep electronics and mechanical systems within usable temperatures during cold Martian nights. The fuel supply fades slowly. Plutonium-238 has a half-life of approximately 87.7 years. After that interval, half of the original radioactive atoms remain undecayed, so the heat output has fallen to about half its starting level. Electrical production declines somewhat faster because thermocouples also age. Their materials change after years of heating and radiation exposure, gradually reducing conversion efficiency. Voyager's engineering teams have managed this shrinking power budget for nearly half a century. Instruments were turned off after the planetary encounters ended. Heaters have been disabled one at a time, sometimes allowing equipment to operate at temperatures lower than its original test limits. Mission controllers continue balancing communication, orientation, and scientific measurements against the remaining supply. The spacecraft survives by doing less than it once could. A crewed vehicle cannot reduce its needs as easily. Carbon dioxide must be removed from the air continuously. Water processors require pumps and heaters. Crop lighting could consume substantial electricity, while medical devices and manufacturing equipment add intermittent peaks. A small habitat might need tens or hundreds of kilowatts. High-powered propulsion could raise demand into the megawatt range. A Voyager-style generator producing a few hundred watts would cover only a tiny fraction of that load. Nuclear fission offers a possible larger source. Inside a fission reactor, atoms such as uranium split after absorbing neutrons. The process releases heat and additional neutrons, allowing a controlled chain reaction to continue. NASA's Kilopower project tested a small experimental reactor in Nevada in 2018. The system used a uranium core and Stirling engines, which converted heat into mechanical motion and then electricity. Designs in this family were intended to produce between roughly 1 and 10 kilowatts. A larger spacecraft reactor would require control equipment, neutron shielding, heat transfer systems, and radiators. Pumps or other moving components would eventually need maintenance. Shielding would have to protect the crew without making the vessel too massive to accelerate. Heat remains important even in distant space. Vacuum contains no cold air that can carry warmth away from the hull. Spacecraft lose heat mainly by emitting infrared radiation from their surfaces. Insulation slows unwanted losses, while radiators release heat produced by occupants, computers, reactors, and life support machinery. A habitat that traps too much warmth can overheat even where sunlight is extremely weak. A damaged radiator could become as serious as a failed heater. The ship therefore carries a finite source of energy while continually managing where that energy becomes heat. Some electricity keeps the crew alive. A smaller share must power the transmitter that sends their voice toward an Earth now separated from them by billions of kilometers. Communication now consumes part of the spacecraft's shrinking electrical supply. A transmitter must produce the signal. A precisely aimed antenna must direct it toward Earth, and receivers on the ground must separate it from natural radio noise. NASA performs much of this work through the Deep Space Network, a group of antenna complexes placed at 3 widely separated locations. The Goldstone Complex stands in California's Mojave Desert, northeast of Barstow. A second complex is located west of Madrid, Spain. The third operates near Canberra, Australia, beside the Tidbinbilla Nature Reserve. These sites are positioned about 120 degrees apart in longitude. As Earth rotates and a spacecraft sinks below the horizon at one complex, another site can rotate into view. This arrangement gives distant missions access to receivers during every part of Earth's day, although individual spacecraft still have to compete for scheduled antenna time. Each complex includes several dishes. The largest is 70 meters across, roughly the width of the wingspan of a large passenger aircraft. Its curved surface reflects incoming radio waves toward a sensitive receiver near the antenna's focus. A transmission from deep space can be extraordinarily faint by the time it arrives. Radio waves spread outward as they travel. At twice the distance, their energy is distributed across about 4 times the area, reducing the received intensity to 1/4. At 10 times the distance, the same signal reaches the receiver with roughly 1/100th of the intensity. Voyager One sends its data through a high-gain antenna, 3.7 meters in diameter. High gain means the dish concentrates most of the radio energy into a narrow beam instead of broadcasting it equally in every direction. The spacecraft's main transmitter produces only about 22 watts, comparable to a small household light. Its normal scientific data rate is approximately 160 bits per second. A modern photograph containing several million bytes would require days to cross that link, even before allowing for scheduling and error correction. A narrow beam also creates a demanding pointing problem. If Voyager's antenna drifts too far away from Earth, the deep space network may lose the signal even while the transmitter continues operating. Small thrusters periodically adjust the spacecraft's orientation so the dish remains aimed toward a target that appears almost point-like from interstellar space. By August of 2026, Voyager One's one-way light time is approaching 24 hours. NASA expects the spacecraft to reach a full light day from Earth on November 18th, when its distance will be about 25.9 billion kilometers. A command, transmitted on that date, will require 24 hours to arrive. If Voyager receives it immediately and sends confirmation back, another 24 hours will pass before engineers know the result. The complete exchange approaches 2 days, even when every system works correctly. During that interval, the spacecraft continues moving and aging. Its temperature may change, a sensor reading may drift, or a fault may spread into another system. Engineers therefore send carefully prepared commands based on information describing the spacecraft's condition nearly a day earlier. The network also measures position and motion. Ranging uses a timed radio signal to estimate distance. The spacecraft receives the signal and sends it back, allowing navigators to measure the round-trip travel time. Doppler tracking examines changes in radio frequency. A spacecraft moving away stretches the received waves slightly, lowering their frequency. Changes in that shift reveal motion along the line between Earth and the vehicle, sometimes with remarkable precision. Both methods still describe the past. At Voyager's distance, the return signal reports where the spacecraft was almost 2 days before the complete measurement reaches the navigation team. A larger antenna can collect more of the faint transmission, and several dishes can combine their observations. More electrical power aboard the spacecraft can strengthen the outgoing signal. These improvements extend communication while leaving the delay untouched. Earth remains available as a source of expertise, software, and carefully written commands. The conversation now unfolds through messages separated by days, with each side responding to conditions that have already moved forward. A crewed vessel traveling still farther would need to navigate during those gaps, recognize equipment failures independently, and decide which course corrections could be made before Earth's advice arrived. A distant spacecraft cannot rely on Earth to describe its present location. By the time a tracking measurement completes the round trip, the vehicle has traveled onward, and any small course error has continued growing. Navigation begins with instruments carried aboard the ship. An inertial measurement unit contains accelerometers and gyroscopes. Accelerometers measure changes in motion. Gyroscopes measure rotation and help determine which direction the spacecraft is facing. Starting from a known position and velocity, a computer adds each measured change to estimate the vehicle's new state. Tiny errors accumulate during this process. An accelerometer may report a minute acceleration while the spacecraft is actually coasting. A gyroscope may slowly drift away from its true orientation. Over several minutes, the difference can remain negligible. Across decades, An error repeated through millions of calculations can place the estimated position far from reality. Star trackers provide an independent reference. These compact cameras photograph patterns of stars and compare them with a catalog stored inside the navigation computer. Once the software identifies several known stars, it can calculate the spacecraft's orientation with great precision and correct part of the accumulated inertial drift. The sky itself changes over long periods. Stars orbit through the Milky Way at different velocities, producing a slow, apparent movement called proper motion. Barnard's star, located about 6 light-years away, shifts across our sky by more than 10 arc-seconds each year, one of the largest known proper motions of any star. Most stars move much less visibly, though decades or centuries can make those small changes important. A long-duration vessel would need a catalog that predicts where its reference stars should appear at future dates. The system would also account for parallax, the apparent shift caused by observing nearby stars from different positions, and for changes created by the spacecraft's own velocity. Its cameras would age during the voyage. Radiation can create dead pixels that stop responding properly. Dust or gradual surface changes may reduce the amount of light reaching the detector. Temperature changes can slightly alter the alignment between the tracker and the spacecraft. Several navigation methods would therefore cross-check one another. The inertial system follows rapid changes in motion. Star trackers correct orientation. Radio ranging from Earth can occasionally refine distance and velocity while the connection remains usable. Each correction has a physical cost. Discovering that the vessel is drifting away from its planned route does not move it back. Thrusters must fire, consuming propellant and changing velocity. A tiny error corrected early may require only a short burn. The same angular error left uncorrected across a light year can produce an enormous miss at the destination. Pulsars may provide a navigation system that remains available far beyond the practical reach of Earth's tracking stations. A pulsar is a rapidly rotating neutron star. Neutron stars form when certain massive stars collapse, compressing more mass than the Sun into a sphere only about 20 kilometers across. Their magnetic fields can direct beams of radiation outward from the magnetic poles. As the star rotates, those beams sweep through space like the beam from a lighthouse. Millisecond pulsars complete hundreds of rotations each second. Their pulse patterns can remain extremely stable, allowing astronomers to predict when individual pulses should arrive. A spacecraft observing several pulsars could compare the measured arrival times with stored predictions. A pulse reaching the vessel slightly earlier or later than expected reveals information about its position. Combining measurements from different directions produces an independent navigational estimate. NASA tested this idea in November of 2017 through the Station Explorer for X-ray timing and navigation technology, known as Sextant. The experiment used the Neutron Star Interior Composition Explorer, or NISA, an X-ray telescope mounted outside the International Space Station. During a 2-day demonstration, NISA observed 4 millisecond pulsars. Onboard software processed 78 measurements and autonomously reconstructed the instrument's path around Earth. The resulting position estimate remained within roughly 5 to 10 kilometers of the station's known location. That accuracy would be insufficient for landing on a small target, though it demonstrated that a spacecraft could calculate its position using natural beacons spread across the galaxy. Future instruments with longer observing times and improved detectors could refine the method. A vessel traveling at a substantial fraction of light speed would face further effects. The apparent positions of stars would shift through relativistic aberration, while their light would change frequency through Doppler shifting. Navigation software would need to account for both. With enough independent measurements, the ship could continue finding its way without constant directions from Earth. Its instruments would maintain a working map, while the solar system behind it became a small part of the sky. That autonomy carries the vessel toward the boundary, where the stream of particles flowing from our star finally gives way to the surrounding interstellar medium. Far beyond the planets, navigation continues through a region shaped by the steady outflow from our star. The solar wind begins in the outer atmosphere of the Sun, where extremely hot gas becomes a plasma. Plasma contains electrically charged particles, mainly protons and electrons, moving fast enough to escape into space. Near Earth, this flow commonly travels at several hundred kilometers per second. The solar wind carries part of the Sun's magnetic field with it. Because the star rotates, those magnetic field lines become wound into a broad spiral across the planetary system. Planets, moons, spacecraft, and drifting dust all travel through this moving environment. The region dominated by that outflow is called the heliosphere. It forms a vast bubble around the planetary system, though its boundary changes with direction and solar activity. The bubble has several distinct layers. The solar wind begins by moving faster than the speed at which disturbances can travel through the plasma. Far beyond Neptune, the pressure of the surrounding interstellar material forces that flow to slow abruptly. This transition is called the termination shock. Voyager One crossed the termination shock in late 2004 at a distance near 94 astronomical units. Voyager 2 reached it in 2007 at roughly 84 astronomical units. 1 astronomical unit is the average distance from Earth to our star, close to 149.6 million kilometers. The different crossing distances showed that the heliosphere is uneven. Pressure from the local interstellar medium, the direction of the Sun's motion through the galaxy, and changing solar activity all affect its shape. Beyond the termination shock lies the heliosheath. Here, the solar wind continues moving outward, though it has slowed and become more turbulent. Particle directions change, magnetic fields become compressed, and the remaining outward pressure gradually approaches the pressure of the surrounding interstellar material. The outer boundary of this region is the heliopause. At the heliopause, the solar wind can no longer dominate the local plasma environment. Material flowing outward from the Sun meets the gas, charged particles, and magnetic field found between nearby stars. There is no solid wall at this boundary. A spacecraft does not pass through a visible surface or experience a single sudden impact. The crossing is identified by changes recorded across several instruments. Voyager 1 crossed the heliopause in August of 2012 at approximately 122 astronomical units from the Sun. Scientists observed a sharp decline in particles associated with the heliosphere, accompanied by an increase in galactic cosmic rays arriving from outside it. Voyager 1's working plasma instrument had already failed decades earlier, so researchers used other evidence as well. Plasma wave measurements detected vibrations produced by passing solar disturbances. Those vibrations allowed scientists to estimate the density of the surrounding material, which was greater than the density inside the heliosphere. Voyager 2 crossed the heliopause in November of 2018 along a different route. Its plasma instrument was still operating, allowing a more direct measurement of the solar wind weakening and the interstellar plasma becoming dominant. Together, the two spacecraft showed that the heliopause can move. Solar eruptions travel outward and alter the pressure inside the heliosphere. Conditions in the surrounding interstellar medium vary by direction. The boundary can shift inward or outward over time, rather than remaining at one permanent distance. Crossing it gives a spacecraft a valid claim to entering interstellar space. The term describes a region where the local environment is controlled more strongly by material between the stars than by the solar wind. The spacecraft, has not escaped the gravitational solar system. The Sun's gravity continues weakening with distance while extending far beyond the heliopause. Objects in the distant Oort cloud are still thought to orbit our star, even though they spend most of their time deep within interstellar space. The inner edge of that cloud may begin somewhere between roughly 2,000 and 5,000 astronomical units away. Its outer regions could extend to 10,000, 50,000, or possibly 100,000 astronomical units, because the cloud has never been observed directly in full. At Voyager One's current speed, reaching the inner Oort cloud would take roughly 300 years. Passing through its broader extent could require around 30,000 years. The heliopause, therefore, marks the end of one solar environment, rather than the final edge of everything belonging to the solar system. A traveler crosses a genuine frontier while remaining gravitationally connected to the star left behind. Beyond that frontier, space still contains matter. The spacecraft enters a thin mixture of gas, plasma, magnetic fields, dust, and energetic particles that becomes increasingly important as the journey continues. Outside the heliopause, the surrounding material becomes easier for Voyager's instruments to measure. This material is called the interstellar medium. It fills the space between stars with a thin mixture of hydrogen, helium, free electrons, dust grains, magnetic fields, and high-energy radiation. Hydrogen is the most common element in the mixture. Some hydrogen atoms remain neutral, meaning they still carry their electron. Others have been ionized, meaning enough energy has removed that electron and left behind a positively charged proton. Helium appears in smaller amounts, along with traces of heavier elements such as carbon, oxygen, silicon, and iron. The density is extremely low by earthly standards. The local interstellar cloud surrounding the solar system contains only around a few tenths of a particle per cubic centimeter. Air near sea level contains roughly 25 quintillion molecules in the same volume. A cubic centimeter of interstellar space may therefore contain less matter than a laboratory vacuum chamber. Yet that material extends continuously across light years. Its temperature can be misleading. Particles in the local interstellar cloud have temperatures of roughly 7,000 degrees. Nearby regions inside the larger local bubble may contain plasma measured at close to 1 million degrees. A spacecraft entering either region would not be heated as though it had entered an oven. Temperature describes the average kinetic energy of individual particles. Heat transfer also depends on how many particles strike an object. In a dense atmosphere, countless molecular collisions transfer energy rapidly. In the interstellar medium, long intervals separate many of those collisions. A small number of energetic particles can produce a high measured temperature while carrying very little total heat. The temperature of a spacecraft is controlled more strongly by radiation and its own machinery. Light absorbed by the hull adds energy. Computers, pumps, reactors, and people generate additional heat inside. Insulation slows the movement of that energy, while external radiators release it as infrared radiation. An unpowered object, exposed to deep space, would cool gradually by radiating energy away. It would not freeze instantly. A functioning crewed vessel might still struggle to remove enough heat because its habitat and power systems operate continuously. The magnetic environment also changes beyond the heliopause. The galaxy contains weak magnetic fields that extend through interstellar gas. These fields are far weaker than the magnetic field near Earth's surface, though they act across enormous distances and influence electrically charged particles. Galactic cosmic rays travel through this environment. Many originate from violent events, such as supernova remnants, where expanding shock waves can accelerate atomic nuclei to extremely high energies. The heliosphere alters part of the cosmic ray population before it reaches the inner solar system. The solar wind and its magnetic field scatter or redirect some lower energy particles. This effect is called heliospheric modulation. Voyager's instruments detected an increase in galactic cosmic rays when the spacecraft crossed into interstellar space. The change helped scientists identify the heliopause, though it did not resemble entry into a single uniform radiation zone. Cosmic ray intensity still varies with particle energy, direction, magnetic conditions, and activity within the galaxy. The highest energy particles can penetrate deeply into spacecraft materials. Shielding produces the same complications seen earlier in the journey. When an energetic nucleus strikes the hull, it may break apart and create secondary particles inside the vehicle. Water, plastics, and other hydrogen-rich materials can reduce parts of the exposure, while no practical passive shield removes the full galactic cosmic ray environment. Researchers have proposed active shielding as well. A powerful magnetic field around a spacecraft could bend the paths of charged particles before they reached the hull. Such a system would require large magnets, substantial electrical power, cooling equipment, and protection from the forces generated by the field itself. Neutral atoms and dust grains would pass through a magnetic shield unless they became ionized first. At Voyager's current speed of roughly 17 kilometers per second relative to the Sun, collisions with interstellar gas generally produce small effects that instruments can study over long periods. Dust can gradually mark exposed surfaces, though the spacecraft does not experience a continuous destructive barrage. A future starship moving at thousands or tens of thousands of kilometers per second would encounter the same medium under very different conditions. The atoms would arrive with far greater energy, and a dust grain too small to see could release a concentrated burst of heat and radiation against the forward shield. Increasing the spacecraft's speed changes those collisions far more dramatically than changing the density of the surrounding medium. A faster crossing offers major advantages. It reduces the number of years that life support equipment must operate, lowers the total time spent under galactic cosmic rays, and shortens the period during which food systems, reactors, electronics, and human institutions can fail. Velocity also increases the energy carried into every impact. At speeds well below the speed of light, kinetic energy is calculated by multiplying 1/2 of an object's mass by the square of its velocity. Because the velocity is squared, doubling the speed produces roughly 4 times as much impact energy. Increasing the speed by a factor of 10 produces about 100 times as much. A dust grain with a mass of 1 microgram is almost invisible. At 10% of light speed, close to 30,000 kilometers per second, that grain would carry roughly 450,000 joules of kinetic energy. This is comparable to the motion energy of a small car traveling at highway speed, concentrated into a particle smaller than a grain of sand. At higher fractions of light speed, the ordinary kinetic energy formula becomes increasingly inaccurate. Relativistic equations are then needed because mass, energy, and velocity no longer follow their familiar low-speed relationships. Interstellar gas creates a more continuous problem. A hydrogen atom has very little mass, but a starship would encounter enormous numbers of atoms during a journey measured in light years. At high relative speed, the atoms striking the forward surface could penetrate material, ionize its atoms, and create showers of secondary radiation. Ionization occurs when a collision removes electrons from atoms. The hull material may briefly become plasma, a mixture of charged ions and free electrons. Repeated impacts could slowly erode the forward shield and expose deeper layers. Dust grains are less common than gas atoms and carry much more mass. When a fast-moving grain strikes the shield, both the grain and part of the surface may vaporize almost instantly. The resulting cloud of hot plasma can spread into nearby material, damage sensors, and create mechanical shock through the structure. Spacecraft in Earth orbit already use a form of protection called a Whipple shield. A thin outer bumper sits some distance ahead of the main pressure wall. When a small piece of orbital debris strikes the bumper, the impact breaks it into a spreading cloud of fragments and vapor. The wider cloud then reaches the rear wall with its energy distributed across a larger area. This method works well for many impacts at orbital velocities of several kilometers per second. An interstellar craft moving at thousands of kilometers per second would operate in a very different energy range. The first layer might create an intense plasma and radiation burst that a conventional rear wall was never designed to absorb. Proposed Starship designs, therefore, use much thicker forward protection. Some include several layers separated by empty gaps. Others place a large block of water, ice, graphite, or another replaceable material ahead of the inhabited section. A sacrificial shield is expected to erode. The ship begins with enough material for part of it to be lost during the crossing. Damaged plates might be moved aside and replaced by fresh sections manufactured aboard. Another concept would release a cloud of fine particles ahead of the spacecraft. Incoming dust could strike this cloud before reaching the hull, breaking apart farther from the vehicle. Maintaining the cloud's position and density during acceleration would require careful control. Magnetic fields could deflect incoming protons, electrons, and ionized gas. Neutral hydrogen atoms and uncharged dust would continue forward until they became ionized or struck physical material. Route surveying may reduce some of the uncertainty. Robotic probes could travel ahead, measuring average gas density and searching for larger concentrations of dust. Telescopes can study the broad properties of the interstellar medium along a proposed path. No survey can locate every microscopic grain across more than 40 trillion kilometers to the nearest stellar system. Shielding must therefore be designed from probabilities, estimated particle sizes, and acceptable levels of damage. The central trade-off remains difficult. Slower travel gives machinery, radiation, and human biology more time to deteriorate. Faster travel raises propulsion demands and turns thin interstellar matter into a stream of high-energy impacts. Even a shield that survives the crossing solves only the cruise. The spacecraft reaches the destination carrying the enormous velocity that made the shorter journey possible, and that velocity must be removed before the crew can remain there. A spacecraft moving at 10% of light speed would cross 1 astronomical unit in about 83 minutes. A planetary system as wide as the orbit of Neptune could pass around it in only a few days. At that velocity, seeing the destination does not mean the crew has reached it. The spacecraft must reduce its speed relative to the target star and any planet it hopes to approach. Without that change, it would pass through the system on a high-speed flyby and continue into interstellar space. This is the difference between arrival and orbital insertion. Orbital insertion is the maneuver that changes a spacecraft's velocity enough for gravity to capture it into a useful orbit. A probe visiting Mars or Jupiter performs this kind of burn after a journey lasting months or years. An interstellar vessel would have to remove thousands or tens of thousands of kilometers per second. The ship gained that momentum during departure. Deceleration must remove it before the destination rushes past. Engineers measure the required change using delta V, the same quantity used for launches, course corrections, and planetary landings. A vessel accelerated to a high cruise speed needs a comparable amount of delta V to slow down, unless it can transfer momentum through some external system. Carrying braking propellant creates a severe mass penalty. That fuel must be present when the spacecraft leaves Earth, so the departure engines must accelerate it, along with the habitat, shielding, supplies, and crew. The tanks holding the propellant add more mass. Larger engines and stronger supports may then be required. Each added kilogram increases the energy needed at departure, producing the same compounding effect described by the rocket equation. Staging can reduce part of this burden. Empty tanks or exhausted engines are discarded after use, allowing the remaining vehicle to continue with less mass. A stage left behind during acceleration cannot assist with braking or return. Every discarded system narrows the capabilities available later. Beamed propulsion moves some of the energy source away from the spacecraft. A powerful laser near Earth could illuminate a reflective sail and accelerate it without requiring the vessel to carry all of its propulsion energy. This approach is often discussed for small robotic probes. A crewed ship would require a much larger sail, an enormous beam, and careful control across great distances. The destination system would probably contain no matching laser array prepared to slow the incoming vessel. A magnetic sail offers a possible braking method. Large loops of superconducting wire could create a magnetic field that interacts with charged particles in the interstellar medium or the stellar wind near the destination. The ship would transfer a small amount of momentum to those particles and gradually decelerate. The force would be weak, so braking might begin far from the target and continue for years. The superconducting system, cooling equipment, and supporting structure would all need to survive the crossing before deployment. Fusion propulsion could provide much higher exhaust velocity than chemical rockets by releasing energy from the merging of light atomic nuclei. Antimatter would offer even greater energy density because matter and antimatter convert much of their mass into energy when they meet. Neither technology currently exists as a complete crewed propulsion system. Antimatter is produced only in microscopic amounts, while controlled fusion has not yet become a practical spacecraft engine. Nuclear pulse concepts would detonate repeated explosive charges behind a large shock-absorbing plate. Studies conducted during Project Orion in the 1950s and 1960s suggested that such vehicles could move very large masses, though engineering, political, and environmental barriers prevented development. Any engine selected for arrival must remain reliable after years or decades of inactivity. Propellant lines must stay sealed. Ignition systems must still function. Sensors must measure thrust accurately, and the vehicle must maintain orientation throughout a burn that may decide the fate of the mission. Relativistic time dilation could reduce the elapsed time experienced by the crew at extremely high velocity. Earth and the destination would still remain separated by the same distance in their shared frame, and the energy needed to accelerate and decelerate the vessel would remain. A return journey repeats the complete problem. The ship must depart the new system, survive another crossing, and remove its velocity near Earth. A design carrying enough capability for only one arrival burn has already become a one-way vessel. The engines may survive, the shield may remain intact, and the destination may appear exactly where navigation predicted. The final maneuver still depends on machinery maintained by people who have spent years keeping the ship alive. Across a long enough voyage, that human community becomes as essential to the spacecraft as its reactor, navigation system, and pressure hull. A voyage lasting decades places the same demand on the crew that it places on the engines. Knowledge, judgment, and cooperation must remain usable when the destination finally comes within reach. Proxima Centauri lies about 4.24 light-years from Earth. At 10% of light speed, the cruise alone would take a little more than 42 years. Acceleration and braking would extend the mission beyond that. At 1% of light speed, the crossing would last more than 420 years. The first crew could spend most of an adult lifetime aboard. A slower vessel would carry people who had never seen Earth directly and had no memory of departure. This changes the meaning of crew selection. The first passengers would choose the mission after years of preparation. Their children would inherit its limits. Several generations later, Earth might exist mainly through stored video, delayed messages, scientific records, and stories taught in classrooms aboard the ship. The vessel would need to reproduce technical skill as reliably as it reproduces oxygen. A reactor technician cannot simply leave behind a manual and assume the next generation will understand every fault. Experienced workers recognize changes through sound, vibration, smell, surface wear, and patterns in sensor readings. Those abilities develop through supervised practice. The ship would need apprenticeships for medicine, electrical repair, navigation, agriculture, software maintenance, and manufacturing. Training could begin years before an older specialist retires. Some fields would require several qualified people so that an illness or accident did not erase an entire area of expertise. Digital archives would preserve drawings, procedures, research papers, and recorded lessons. The computers holding those records would need migration to new hardware as storage devices aged. File formats and operating systems could become unreadable unless each generation actively maintained them. Population size creates another constraint. A very small population uses less food, water, living volume, and electrical power. It also carries less genetic diversity and fewer people capable of covering essential jobs. A larger population improves redundancy, while placing greater demand on farms, life support, medical supplies, and habitat space. Researchers have proposed widely different minimum populations for generation ships because the result depends on assumptions about voyage length, stored embryos, reproductive planning, medical technology, and the acceptable risk of losing rare skills. There is no single proven number. Human isolation studies provide only partial guidance. Mars 500 placed 6 men inside a sealed facility in Moscow for 520 days between 2010 and 2011. The experiment simulated a Mars mission with delayed communication, restricted living space, and a carefully planned schedule. Antarctic research stations can remain cut off for months during winter. Submarines carry crews into confined environments with limited privacy and artificial day-night schedules. Astronauts have lived aboard orbital stations for more than a year. None of these settings reproduces permanent separation from Earth. Participants know the experiment will end. Rescue remains possible under some conditions, and the outside world continues nearby. Sleep would become a practical safety issue. Noise from pumps and ventilation could continue throughout the artificial night. Shift work might separate crew members into different daily schedules. Light exposure would have to regulate body clocks in a habitat with no natural sunrise. Privacy would remain limited. The same colleagues could share meals, maintenance duties, disagreements, and emergencies for decades. Monotony can reduce alertness, even when no major conflict occurs. A small misunderstanding left unresolved could affect teamwork in a control room or repair bay years later. Governance would shape survival directly. The community would need rules for allocating scarce resources, assigning difficult work, managing reproduction, and responding to people who rejected the mission's goals. There would be no nearby country to accept emigrants and no outside court able to enforce a decision quickly. Cultural priorities could also change. Descendants might value the stability of the ship more than the original promise of settlement. A later mission launched from Earth with faster propulsion could even overtake the older vessel, arriving first despite departing decades afterward. That possibility could alter morale and the purpose attached to the journey. NASA already studies isolation, sleep, cognition, and team performance because a Mars crew will depend heavily on local decision-making. An interstellar vessel would turn those concerns into permanent operating conditions. The community aboard would become part of the spacecraft's machinery. Its schools preserve technical capacity. Its institutions maintain cooperation, while its health determines whether critical work can continue. A ship could preserve all of those systems across centuries and still arrive with no guarantee that the world ahead can support human life. The nearest known planet that might offer familiar conditions orbits Proxima Centauri, the closest star to our solar system. Proxima Centauri lies approximately 4.24 light-years from Earth. The planet, called Proxima Centauri b, was announced in 2016 after astronomers measured a repeated motion in the star. The planet's gravity pulls slightly on Proxima Centauri as the two bodies orbit their shared center of mass, causing the star to move toward and away from Earth by a small amount. Proxima b completes one orbit in about 11.2 days. Its orbit lies within the star's nominal habitable zone, the range of distances where temperatures might allow liquid water on a planet's surface under suitable atmospheric conditions. That definition carries several uncertainties. A planet in the habitable zone may have no atmosphere at all. A thick atmosphere could trap enough heat to make the surface hostile, while a thin one might allow water to freeze or escape. The term provides no evidence of breathable oxygen, oceans, biology, or a safe place to land. Proxima Centauri is a red dwarf, with only about 12% of the Sun's mass. Because it produces much less total light, Proxima b must orbit extremely close to receive enough energy for possible liquid water. The planet travels only about 7 million kilometers from its star, roughly 1/20th of the distance between Earth and the Sun. That closeness exposes it to the activity of the red dwarf. Proxima Centauri produces powerful flares that release ultraviolet radiation, X-rays, and energetic particles. In March of 2016, astronomers recorded a flare that briefly made the star many times brighter at millimeter wavelengths. Other observations have shown that smaller eruptions occur frequently. High-energy radiation can break molecules apart in a planet's upper atmosphere. Charged particles may then be carried away by the stellar wind, gradually thinning the atmosphere through a process called atmospheric escape. Computer models have examined whether an Earth-like atmosphere could survive under these conditions. Some results suggest that atmospheric loss could occur far more rapidly than it does on Earth, especially if the planet lacks a strong magnetic field. The actual outcome depends on the atmosphere's original thickness, chemical composition, volcanic activity, and magnetic protection. None of those properties has been measured well enough to tell a crew what the surface would be like. The planet may also be tidally locked. This would mean that one hemisphere continually faces the star, while the opposite side remains in darkness. A substantial atmosphere or ocean could move heat between the two sides. Without enough circulation, temperatures might differ sharply across the planet. Other systems offer more planets while greatly increasing the journey. TRAPPIST-1 lies roughly 40 light-years away. It contains 7 known planets, similar in size to Earth, all orbiting a cool red dwarf. Several receive amounts of starlight that place them near or within estimates of the habitable zone. Astronomers study these worlds through transit spectroscopy. When a planet passes in front of its star, a small amount of starlight may filter through the atmosphere. Different gases absorb specific wavelengths, leaving faint patterns in the measured spectrum. The signal is extremely small. Clouds can hide deeper atmospheric layers. Activity on the star can create patterns that resemble a planetary signal, a problem known as stellar contamination. Repeated observations may narrow the possible atmosphere while still leaving its surface pressure, weather, and magnetic field uncertain. Future space telescopes may directly image some nearby rocky planets by blocking the overwhelming glare of their stars. Robotic precursor missions could eventually provide much better measurements before humans departed. A probe reaching another star would still require decades or centuries with foreseeable propulsion, allowing the destination to change before a crew arrived. The vessel could enter the system and find a planet with no useful atmosphere. Accessible water might be locked beneath kilometers of ice, while radiation makes surface work dangerous. The best world could lack an area where a large spacecraft can land or gather enough material to replace its supplies. In that case, the ship would remain the settlement. Its aging pressure hull would continue holding the atmosphere. Its reactor would still power the farms, and every repair system developed during the crossing would remain essential after arrival. Earth might eventually receive a message describing what the travelers found. That message could cross 4 light years and reach home years after the discovery. No vehicle from Earth could arrive in time to change the outcome. The astronauts aboard the International Space Station also appear alone against black space. Beneath them, Earth tracks their orbit, answers their voices, prepares replacement parts, and waits for their return. Each boundary beyond that orbit transfers more responsibility from the planet to the spacecraft. Distance makes fewer failures temporary. Far enough away, every serious emergency must be solved using the people, materials, and knowledge already aboard. The promise of another world can only be tested after the travelers have crossed the point where returning is easy, and perhaps the point where returning remains possible at all.